So once again, we have harmonic functions in kink elliptic PDE. And we have a nice part of the domain, nice open part, relatively open on the boundary. And I said that the problem when function is 0 here and the gradient is 0 on a subset of positive measure is solved for different classes of the domain. But even more elementary result is that if you function it in the normal derivative vanish on this open set, then the Cauchy uniqueness theorem tells us that function is 0. And there is a quantitative version of this theorem that tells you that if your function is small on fixed open part of the boundary, and say the gradient of the functions is also small. So here is my domain, here is part of the boundary. Oh, then there is a version of 3 Ball's theorem saying that the maximum, say over this ball V, let me take a bit smaller ball so that we have boundary while is intersection of V times, and take half ball here. The maximum of our function there is bounded by constant this smallness to some power times the maximum of U over, say, whole domain. One of the proofs, probably the first proof that I know in the literature, is due to von Lin, and used Coleman inequalities to prove this result in higher dimensions. And for harmonic functions and say nice flat bound here, you can do it much easier. It's a nice exercise, and if you want to read it for this case, it's written in our recent preprint with Loganov, Nazarov, and Nadirashvili. This Cauchy, quantitative Cauchy uniqueness has another implication for the distribution of a frequency function, and it's another nice lemma of Loganov. Let me think about function defined in a unit ball, and we'll suppose that there are many balls on the plane, hyperplane through the origin where the frequency is large. Then we say that the frequency on the ball here is even larger. So let me write something like that. So D intersect with the hyperplane xn equals 0 is covered by some balls of fixed radii here, and then we say that the frequency is larger than constant times the minimum of the frequencies. And this is the second tool to control the distribution of places where the frequency is high, together with simplex lemma, tells you that, roughly speaking, in a cube of like that, if you divide it into very small cubes, there is not just one cube where the frequency is less than the maximum frequency over 2, but most of them, the cubes for which the frequency is larger than maximum over 2, if you divide everything into b to the power d cubes, you'll get less than d to d minus 1 with a small constant. And then iterations of that give you even a little bit smaller power than d minus 1 here, just by iterations. And this was their tool to prove unique continuation from sets of dimension larger than d minus 1. So we needed this estimate that there is less than d minus 1 portion of this cube with this one. When we want to discuss propagation of smallness for the gradients instead of the function itself, we hope that there is something that can be done as soon as the condimension is larger than 2. But to repeat the procedure that we had, we don't have enough information here about the distribution of frequency to go to something that is a little bit worse than d minus 2 there. It would be nice to have more results on the distribution of frequency to know that it's not like that. I believe that actually this function, you can say much more about it that we currently know. It's a very nice function of d plus 1 variables with limit that has some geometric meaning as the vanishing order of the function. But there should be more about this function that we still don't understand the behavior on different scales and so on. Okay, let us go back to the estimate. I have a holomorphic function, not holomorphic function, but have a function from the union disk to complex number that satisfy this inequality. And I want to estimate the number of critical points. By constant times. I want to use Carl-Lemon inequality, and the weight that we will take is the following. It will be a constant times, let me write z here, z squared minus some log. So let z1 the jb zk be the zeros, sorry, a1 ak are the zeros yes, it's a holomorphic function, so what I'm going to estimate is the number of zeros of this one in a smaller mole. And once again, I'm going to do it several times. So on the first step, take only zeros that are close to the origin. In the ball of radius 1/10. Here it will be more important than in our previous argument. And the coefficient here I want to write as a product of a that is an absolute constant that I'll choose a bit later, times k that is the number of the terms here. This is a nice function, but it has singularities at aj. The Laplace is nice and positive everywhere except those points. So I will apply the Kerr-Lehmann estimate to this weight and function u that doesn't see these points, that is 0 around those points. So take function g epsilon, x positive epsilon, and take g epsilon so that it's between 0 and 1. Smooth and nice function. It should be 0 on disks of radius epsilon around each point, each 0, and it should be 1 on 3/4 of the disk minus two balls around those points, radius 2 epsilon. Epsilon will go to 0 at the end. You can think that I fixed my function f. There are different zeros with multiplicities. If I have the same 0 here with several multiplicities, I will put the terms here, but the distinct zeros are on some positive distance from each other. Take epsilon that is much smaller than this distance, so that we have a nice picture. This is a small disk, those are zeros, and these are disks of radius epsilon around those. In addition, we know that we can do it such that the gradient of g epsilon bounded by constant over epsilon b. And those are the places where our function goes from 0 to 1 or from 1 to 0, and where we can do it. So this is a standard cutoff function, and we will apply the Kerr-Lehmann inequality to function u that is f times g. Let us write it down. The Laplacian of phi on this set is just equal, on the support of u, just equal to 4at. So our inequality should be something like that, d bar u e phi squared over d is larger than Laplacian over 4. This one. I have two terms here when I apply d bar g. Sorry, I forgot one important thing. I need my parameter Ra to be present in this estimate. So we'll estimate the number of zeros by the frequency plus a squared here. And the first step is, I suppose that k is large enough, larger than constant times a squared, then we can absorb the second term into the right-hand side. If k is large, then this part that is bounded by a squared times f squared in this integral can be absorbed, and we can forget about this one and put 1/2 here. Remember, this small a is a fixed constant that I'll choose later. Yes.
Did you say so from the second line to the third line should there be a greater than or equal to, or are we adding the
From this line to that line,
yes.
I just write d bar of the product as sum of the two terms.
Oh.
Right? I write d bar on G and then on F. Here in analytic case, there is no plot here, but Kerleman inequalities are very nice that they allow you to work with differential inequalities, not differential equations. And in situations, you can absorb these terms by the right-hand side. So I have this one, I just need to control this d bar, I don't need this term to disappear. Next, let us see where our gradient of G lives. It's only a ring, outer ring where G goes from 1 to 0 and a small ring around each 0. So in the left-hand side, we have two kinds of terms. I think what I did was Kerleman inequality with a wrong sign, and you never caught me. So there is a weighted estimate for the operator by the function itself. And then this term is bounded by half of this one, so if this inequality holds, we should be able to bound this one by. What am I doing? No, sorry. I think it was right? So our identity was that this one is positive sinc plus that one. This is the right inequality. And this is less than half this one. Yeah, sorry. Yes. This was right in the beginning. And now I'm rewriting the terms with d bar. Two of them, one is between 1 and 3/4. And we agreed that d bar is bounded by 5. Don't know why 5, but why not? And then it's the part around each 0. Where d bar of G is bounded by 2 times 1 over epsilon. And in this side, let me take a smaller integral. I'll integrate only over z with absolute value between 1/4 and 1/2. Function g is equal to 1 there. We're far from our cutoff regions. and this is the inequality. So now I want to compare the first term to the right-hand side. Let us look at our weight function, 5x, 5z. It was akz squared minus some log z minus aj. So I want to absorb the first term into this one. So I want to show that this is small enough. Let us look at the maximal value of the weight on this disk. So the maximum when z is between 3/4 and 1, 5z. The first term is bounded by a times k, and then we I'm thinking if the sign is right or not, but we'll see it in a moment. Then we have the terms that are negative because we're in the unit disk. The distance from 1 to, no, probably not negative, but okay. So what is the largest term here? So what is the smallest value here? The smallest value is 3/4 minus 1/10. Hopefully I'm right, but you can think about it. This is the maximal value of my weight on the left-hand side. Now let us go here and see what is the minimum weight on the right-hand side. So the minimum is between 1/2, 1/4 and 1/2 of z. I'll forget about the first term. And I'll say that here the largest thing that we can get is 1/2 plus 1/10. That is still less than this one. So now I choose my A to be sure that this is constant times W2, this is constant times W1. A is such that this one is less than this one. So my inequality is constant e to k W2 integral over here plus some let me write this integral a bit more careful. F squared e to a k z squared over the product of the terms z minus j and the absolute value larger than or equal to a k over 2 z 1/2 1/4. The exponential factor e k double 1/2 squared z 1/2 1/4. Now the ratio of those two terms is the frequency function. It's bounded by the frequency function, the doubling index. So I know that this is not too small compared to this one. I know that this integral is now that this integral is larger than that one times e to some power times k. And I'm saying that if k is larger than the constant times the frequency of f 0, 1 plus 1, then I can absorb this term into the right-hand side. Just choosing this constant large enough. If k is larger than the constant time the frequency, we don't care about this term. And then we're done, because now we have those integrals. In each of them, nice thing is that f is 0 around this point. So now try to think what happens when epsilon goes to 0. When epsilon goes to 0, I'm integrating over a small area around this point. I'm dividing by the factor that is proportional to the area of integration. But my function of f squared here divided by 0, it's 0 near this point. So when epsilon goes to 0, this term vanishes, it goes to 0. And we get a contradiction using the inequality. Right, so this goes to 0 when epsilon goes to 0. We have something non-zero on this side, and we conclude that our assumption that the number of zeros was large enough is not true, and there is no way our function has so many zeros in this small discrete radius 1 over time. Any questions about this proof?
Can you figure out why we get the feedback plus a squared?
The a squared comes from the first reduction where I wanted to absorb the term with d bar f by the right-hand side. It's, as I said, it's still a toy problem. There are other ways to get this bound in a more elementary way, but it's a nice thing that you can fit on the blackboard and explain how Cardamon inequalities work using these cutoff functions and nice doubling inequalities. Any other questions about the proof? If not, I will start to prepare some things for the main story that we will have on Thursday. And it's an estimate of what is called effective critical set. I will not give you all the details of Naber and Valtorta paper, but I'll tell you most of the previous paper by Chigir, Naber and Valtorta, at least. And I'm thinking of doing most of it in dimension 2, though the result holds in high dimension. Let me the idea is to get quantitative estimates on the size of the critical set, or what they call effective critical set. It's roughly speaking neighborhood of a critical set using the frequency function. And the estimate that they get at the end is exponential in the frequency, and we're not going to check all the computations and end up with this. What I want to start with are two nice observations. The first observation is that our frequency function is monotone, it's increasing. And in a sense, it's strictly monotone. If it's a constant over some interval, then our function is a polynomial. And there is a quantitative way to say it. Let us fix a radius between 0 and 1. There is positive epsilon such that if, let us take upper frequency function, and suppose that it's bounded by epsilon, the difference between the upper frequency function level 1 and R. Then we claim that we can approximate, I need one more parameter, fix positive eta and R there. Then you can find epsilon such that this inequality implies that you can approximate your function by a polynomial in a nice way. So there is a homogeneous harmonic polynomial P such that I need one more sink probably. I will fix those parameters and capital N. We assume that this is bounded by epsilon, but also the frequency is bounded by N. Then the difference between function U and this homogeneous harmonic polynomial, say on the boundary of the unit ball, is bounded by the normal of this function. And I guess the best thing would be to subtract the value at 0. Let me assume that the function is 0 at 0 just to avoid this constant thing. Our frequency is constructed such that we subtract this constant anyway. So if the frequency is almost constant, then the function is close to harmonic polynomial. There is a more quantitative version of this statement in the second paper of Naber and Valtorta. They compute the derivative of the frequency function and know that if your frequency is not integer, you have an estimate for the derivative from below using the distance from the value of the function to the integer. I don't think it's a computation that you want to do on the blackboard, but it's a nice thing to do by yourself. Just from the formula for the frequency, you can do it. So the only thing, the frequency is not changing much over some longer interval is when this is an integer number and this is the degree of the polynomial but which we want to approximate. Now, if you think that we have a function with bounded frequency and we'll look at it at many scales, take geometric series of scales, since your total frequency is bounded, there are many situations where from one scale to another one, your difference is small. You can bound the number of jumps of the frequency, number of the steps by the log of, by the constant times this n. And if you have many scales in most of them, you will see that your function looks like a polynomial. And there is another.
So what do you know of the
Sorry?
What do you know of the degree of the polynomial?
The degree of the polynomial would be the frequency, this value, the value here. Right. So the second part of the nice argument how the things are, it's the simplest way is to do it in dimension 2. Let us first have the following observation. Suppose that we have a homogeneous harmonic polynomial in dimension 2. That is also homogeneous harmonic polynomial with another center. So let P and Q be two homogeneous harmonic polynomials such that Q of x is equal to Q of x minus x0. Then they're linear. Then the degree of the polynomials is equal to 1. You can, for example, imagine the zero set of homogeneous harmonic polynomials. It's very simple in dimension 2, and see that the only case you have this if those are on the same line, and this line is the zero set of the polynomials. This is not true in higher dimensions. You can have situation where the harmonic polynomial, for example, in R3 depends only on two coordinates. And you go along one of them and you have harmonic polynomials of any degree depending on two polynomials. So in higher dimensions, what Naber and Valtorta, Chigov, Naber and Valtorta do, they divide the critical set where your main term up to the constant that we subtracted is not linear into the family of sets depending on how many essential variables are there. In dimension 2, at any critical point where the gradient is 0, the main harmonic polynomial depends on two variables. In higher dimensions, it depends at least on two variables. It could be 2, 3, and so on up to the full dimension, and the set where the gradient is 0 is divided into these parts. And for each of them, you can try to estimate the corresponding set. So what I can probably do is to introduce a notation that you can try to think about till Thursday. After we introduce the upper frequency, we know that the limit when R goes to 0 of the upper frequency is at least 2 in my notation. Remember, it's twice the vanishing order. And at the points where the gradient is 0, it's at least 4. So for each x, define Rx such that Rx is the infimum R for which at critical points where the limit is at least 4, we will have this R to be 0. Basically, what we will estimate as effective critical set, let me call it, this is set of points, for example, in half of the ball, but everything will be local, so it's not important, such that R of x you can think about it as a neighborhood of the critical point. The critical points, if my inequalities are correct, the critical point, this is 0, so they are in the intersection of these sets. And when you take R smaller, your set is smaller. So this is a family of neighborhoods of the critical set. And this is not the definition of Liebherr-Voltorte, but it's basically what they estimate the size of this set where you have this control of the function. So I'll try to explain you on Thursday how using these two things in dimension 2 at least, you can try to estimate the size of this set and show that this is the critical set has Minkowski dimension 0 in dimension 2, in higher dimensions, Minkowski dimension of n minus 2, how to do the estimate, and also use it as the starting point for our induction argument, how to do propagation of smallness from sets of codimension at a bit smaller than 1, a bit larger than 1, codimension a bit larger than 1. But there are more problems in this results than answers. The result of Liebherr and Voltorte, roughly speaking, for this set would be that the volume is good bounded would be d minus 2. I'm not sure we'll get there, but at least d minus 2 plus small epsilon. But the coefficient that is here in terms of the frequency function, it's like exponent of n squared. And philosophically, there is no reason why it should be so bad. Most probably, this is the method that gives us such crude estimates, and it would be nice to have a better control. We know that in dimension 2, the critical set itself, its n points. If you take effective critical sets, it's not just n times r squared, it's actually n squared times r squared. You can place these points such that they produce a bit larger effective critical set, but still there is some polynomial bound in dimension 2 for nice equations. I think it would be nice to understand if there is a better bound in higher dimensions for this set. I'll stop it here and hope that you'll digest some of it till Thursday, and we will try to do the most boring part, most technical.